All right, now we're going to address a point that we sort of glossed over in the previous discussion of symmetry, and that is the fact that we make measurements in the laboratory frame, and yet the symmetry that we were describing only offers simplification in the local frame. So how do we bridge those two frames to really fully take advantage of the local symmetry that's possible? And that's going to be the topic of this section, and that is reference frame rotation of the Mueller tensor. How do we go from the laboratory frame where we make the measurements to the local frame where we can take advantage of simplifying symmetry relationships? And we're going to assume that there's only, because everything in a Stokes and Mueller framework is defined exclusively in a two-dimensional system of polarization space, so we really only have horizontal and vertical. So we're going to refer to everything in terms of the horizontal and vertical axes in terms of the Stokes, Jones, and Mueller frameworks. And anytime we go to Cartesian coordinates, I'll let you know. So in this case, we're considering there's only one orientation angle that has to be considered, and that's azimuthal orientation by the angle phi. So if we rotate, have some relationship connecting h prime to h by this rotation angle phi, then for the Jones vector, if you just want to relate some vector property in the Jones reference frame from the HV reference frame to the H prime V prime reference frame, you do that through a standard 2x2 rotation matrix. So this would be, for example, rotating a Jones vector. If we want to rotate a Stokes vector, well, we're going to do this the exact same way that we talked about for symmetry operations, where we're just going to consider the rotation as a particular class of symmetry operations. In other words, where we had 1, 0, 0, minus 1 in our symmetry matrix for mirror plane reflection, we're just going to put the rotation matrix because that is actually a symmetry operation as well. It just doesn't happen to, well, I'll just leave it at that. So we can think of this as yet another application of symmetry. And so we have the exact same sort of relationship bridging the Jones rotation operation to rotation of a Stokes vector, which we will then use to rotate the Mueller tensor. So when you multiply all of that out, you end up with this expression for this swirly R. The script for the R is meant to indicate that it's a 4x4 matrix, rotation matrix, that rotates the Stokes vector as opposed to the 2x2 that we had to rotate the Jones vector. All right, and that's all well and good. We now have a way of rotating reference frames. How do we apply this? If we think back to linear optics, we can do that by incorporating these rotation matrices into the Mueller framework. So we can imagine we've got some input in the laboratory frame. We rotate into the local frame, let M operate in the local reference frame where symmetry can reduce the number of non-zero elements, and then rotate back to the laboratory frame, and that will then give us the output for our Stokes vector. And so then, therefore, the rotated M is related to the M that is unrotated in the local reference frame through this simple operation set of products, simple set of matrices. We can do the exact same thing in, and if we in the limited non-depolarization, we can substitute in for this M0 and reference that and put that in the context of the Jones framework. But again, that's only the rest of the analysis I'll be describing doesn't actually hinge on the ability to connect back to the Jones. And that just hits one additional degree of simplification in the limit of non-depolarizing interactions. So if we look at how we can generalize this for the Jones tensor, for the Mueller tensor, I won't go through the derivation. I'll just give you the final output. It's really quite intuitive. It's exactly analogous to the linear case, except we have to rotate two fields into the local reference frame, let the Mueller tensor operate in the local reference frame, and then rotate back to the laboratory frame. And that gives us our laboratory frame measurement in terms of the symmetry allowed elements within the local frame Mueller tensor. All right. And something about vectorization. So it turns out that if we use a vectorized notation for the Mueller tensor, This whole thing is actually considerably simpler because the rotation matrices, you can link the local frame tensor, the full set of 27 elements in the local, 64 elements in the local frame tensor element, to the full set of 64 in the laboratory frame by, if these are vectorized, then you can just relate it as a matrix product of these. There would be a 64 by 64 Kronecker product of rotation matrices, and that allows you to bridge one-to-one local frame to laboratory frame tensor elements. Now, I mentioned that there's simplification possible in the local frame Mueller tensor, and eventually what we're going to want to do is invert all of these equations and solve for the local frame Mueller tensor. And in that case, there's a lot of zeros in here, and we can, so because there's 20 non-zero unique elements, but there's 64 possible total elements, and in fact, in order for the dimensions to work out in this product, this has to be a 64 element vector containing all elements, whether they're zero or not, in the local frame tensor, so we can rotate it over and get the laboratory frame tensor elements. But we can populate the full set of 64 with a subset that are unique if we introduce a symmetry matrix. And that symmetry matrix, we're just going to say, we've got 20 of these that are non-zero and unique. We'll just populate all 64 with a 64 by 20 matrix that is, have a lot of zeros in it, but basically will allow us to generate all 64 of these and connect up all of the equalities to just have a set of unique non-zero elements in ML. And that now gives us something where we've got 64 elements on this side, and inside ML here, we've got 20 elements. So that's a big advantage in terms of dimension reduction. And the next step is to, I think we actually have, eventually what we'll do is figure out how to populate all that full set of hues. Oh, dear Lord. That's a good place to stop.